Now we turn to the topic of locality, which we already mentioned in the previous slide. Common sense tells us that there is no direct influence between the events that are separated by very large distance and very large time in a given frame of reference. However, if we naively combine these two ingredients of discreteness and Lorentz invariance, this is exactly the implication we get. As we saw on the previous slide, events near the light cone arbitrarily far away in the distance and time can be directly related to the central point. If this happens, then physics is non-local. Just like physics appears to be Lorentz invariant according to our current experiment, it also appears to be local at classical level. Of course, there is quantum theoretic version of non-locality involving things like entanglement, which we are quite familiar with. All these type of non-locality seems to conspire to preserve reasonable properties of classical physics. For example, by preventing communication faster than the speed of light, by prohibiting cloning of quantum states. When we talk about locality, we are talking about classical locality in single space-time, not the more subtle notion of superimposed spacetimes. When we move from conventional continuum-based physics to a discrete context, there is a trade-off between Lorentz invariance and locality. If a discrete directed set D is sufficiently Lorentz invariant, then it is very non-local. We saw an example of this involving sprinkle causal set on the previous slide. If we assume Lorentz invariance, then all the red and white elements are directly related to the central element and locality fails spectacularly. On the other hand, if D is sufficiently local, then it strongly violates Lorentz invariance. The easiest example of this is a lattice, which has a single God-given frame of reference in which each row of the horizontal element is mutually simultaneous. The lattice has no non-local behavior because it requires many steps to get from a given element to another element that is far away both in space and time. But its extreme violation of Lorentz invariance places it at odds with the observation. We would like to offer an analogy about the relationship between Lorentz invariance and locality based on the familiar uncertainty principle. This analogy is not intended to be mathematically precise, although some type of precise relationship might be possible for certain configuration space. The most iconic version of uncertainty principle involves relationship between position and momentum for a single particle in ordinary quantum theory. Particle states that have certain position, namely position eigenstate, have uncertain momentum, while momentum eigenstate have uncertain position. However, the overall state space that describes the possible behavior of the particle includes both types of eigenstates and also includes many other states defined by superposition which have some combination of uncertainty in both position and momentum. Turning back to the relationship between Lorentz invariant and locality, quantum gravity suggests that we need to combine contribution from all the directed sets in an appropriate configuration space, and it is difficult to imagine that all these directed sets will either be approximately Lorentz invariant or approximately local. Instead, we should expect that the configuration space will include certain directed sets such as sprinkle causal sets which are very Lorentz invariant and very non-local, or as well as the other directed sets which are very local but strongly violate Lorentz invariance. We can metaphorically refer the first type of set as Lorentz invariance eigenstate and the second type as locality eigenstate. However, the overall configuration space will include many other directed sets as well, and the quantum world will incorporate them all. It may be that different type of observation will detect Lorentz invariance and locality just as different type of observation detect position value and momentum values. In terms of trying to observe deviation from these properties, the moral seems to be that we need a sufficient balance of size and energy for our experiments. Just like we did for Lorentz invariance, we can ask constraint involving locality should make us reject discrete space-time model entirely. Fortunately, the answer is no, although such constraints do pose potential problem for models that exhibit extreme degree of non-locality such as directed sets constructed by sprinkling. However, this is not such a bad state of affairs because we do not expect physically realistic directed space-time models to be merely induced by some imaginary manifold structure. Instead, we expect manifold structure to be an emergent consequence of discrete models that are likely not very manifold, like below some critical scale. In other words, locality constraints pose a serious problem in the context only if we insist that discrete models exhibit no essentially new behavior beyond what we see in general relativity. On the other hand, discrete spacetime models cannot all be too local, or they would violate Lorentz invariance to a degree that has already been ruled out by observation. Hence, we expect classical locality will break down at some scale. This has been well recognized in causal set theory for some time. Intriguingly, it has been proposed that the scale involved might be within present or near-term experimental reach. We include a quote from Shorkin here, who suggested the possibility that noticeable non-locality might be detectable at a scale as large as 10 to the power negative 14 meters, and even poses the question of whether existing observational data might offer evidence about this if we can decide what to look for. If the classical locality does break down, then how might we detect it? Most of the suggestion offered in literature involves the dynamics of some sort of auxiliary structure associated with a directed set, such as scalar field in causal set theory. Here we illustrate some simple examples of such fields, which are given by assigning numbers to elements or relation of a directed set. We could be more sophisticated and work with operator fields, but integer value fields suffice for our purpose of illustration. There is a considerable literature devoted to describing the dynamics of such field in terms of non-local operators, and non-local behavior could conceivably be detected by testing such dynamics. This would require us to translate information about such fields into more familiar statement involving established physics. Also, if the strong version of causal metric hypothesis is true, then we might have no auxiliary structure to work with. However, it is not out of the realms of possibility that some concrete tests could emerge from this line of research in near future. Now we recap the main purpose of our presentation. Space-time models involving discreteness and causal structure are promising for studying quantum gravity. The general theory of directed set may be applied to many more specific models like spin foam, causal dynamic triangulation, and causal set. Classical observation in a single space-time may be defined in terms of subobject of such sets. The theory of relation space is useful for describing the ideal observation since it solves the problem of permeability. Effective observation, which involves the storage of information, may be understood in terms of entropy. Quantum observation involves ensemble of classical observation. Lorentz invariance and localities are both strongly supported by experiment, but a new viewpoint regarding these properties is necessary in discrete context. We must study Lorentz invariance in terms of emergent symmetries because no discrete object has continuous symmetries. Observing violation of Lorentz invariance requires some combination of size and energy for experiments. There is a trade-off between Lorentz invariance and locality in the sense that a discrete directed that strongly obeys one property strongly violates the other. It is possible that classical non-locality might be testable in near future if space-time is really discrete in fundamental scale. Thank you so much for watching. The last few slides contains our references. We will not read them off because you have the access to the presentation slide itself. Have a wonderful day.